In this video, I'm going to compute the derivative of the sine function. So it's going to take a bunch of steps. It's going to be what I like to call sometimes a wall of algebra. And it's also going to use some facts that we learned back in the limit unit. It's going to use some properties of the limit, and it's going to use one of the trig identities that is on our reference sheet. None of those Most of those are things that you don't need to know in order to have a full life as a calculus student. But let's take a look at how you go through step by step and do this thing. All right, so here are the basic facts. Back in the limit unit, when we were talking about this was the first limit that we calculated just looking at tables. And it's also something that we analyzed when we looked at the squeeze theorem. So the limit as x approaches 0 of sine x over x is equal to 1. All right, and the thing that went along with this, we talked about in the squeeze theorem video, is that the limit as x approaches 0 of cosine x minus 1 over x is equal to 0. This is something that is good to know. So that's a handy thing to memorize. This is not a particularly handy thing to memorize. And another thing, if you happen to have studied trig in some detail, you know the sine sum identity, which is that the sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So we're going to use these 3 steps plus a few limit properties to calculate the derivative of sine. So let me, rather than writing it out and risking making a mistake, I went through and double checked my work at every step. So we are just going to reveal this step by step. So the first thing we do when we calculate a derivative is we start as we always do with the definition. So the derivative is the limit of a difference quotient function. The limit as h approaches 0 of sine of x plus h minus sine of x over h. So the first thing we normally do going on from here is that we evaluate these two functions. So, if f of x was x cubed, then this would be x plus h quantity cubed, and this would be x cubed. With sine, it's a little bit harder to kind of work that out. And sine of x, we can't simplify that any. So what we can do, though, is we can simplify sine of x plus h. I don't know that it's simplified, but we can expand this using the trig identity that we mentioned here that we started out with. So this becomes the limit as h approaches 0 of sine x cosine h plus cosine x sine h. And then I'm bringing along the minus sine x, and all of that is over h. Okay, so all I did there was expand the sine of x plus h into this thing right here. What I'm going to do next is one of the limit properties that we know, which is that I can break a limit into if I break this into the sum of 2 equivalent expressions, I can calculate 2 different limits, the limit of one part and then the limit of the other part. And so it'll be obvious why I'm doing this in a few moments, I think. But what I'm doing is I'm collecting this term and having that be in the first expression. And then the other expression is cosine x sine h. And both of those are over h. Okay, so all I'm doing is taking this one limit and turning it into 2 limits. So it's in one idea, it's double the work, but in another idea, these are both going to be simpler to calculate. The next thing I'm going to do is I'm going to collect some like terms and just write this in a slightly different way, because both of these terms have a sine x in them. So I'm going to gather out that sine x and have it be outside of the fraction. So when I factor out that sine x, the fraction becomes cosine h minus 1 over h. And then I'm going to do the same thing with cosine x on this side. I'm going to bring the cosine of x outside the fraction. So it's cosine of x times sine h over h. Now, we're going to use another limit property right now, and this one's a little tricky, so take your time and think through this. So sine x doesn't change when h is approaching 0. When I'm thinking about different values of this expression, when h is 1 and 0.1 and 0.01 and 0.000001 and whatever, getting closer and closer to 0, sine x itself doesn't change. All right, so this, even though it's got a variable in it, within the context of this limit statement, sine x is a constant. All right, so I determined what x was way up here, and inside this limit expression, sine x isn't changing. Same thing is going on with the cosine x in this expression. This is an expression that only talks about the limit as h approaches 0. So the cosine of x is a constant in this expression. So what we can do is, since these are constant expressions, we can move them outside of the limit. That's another one of our limit properties, is that when we've got constants inside the limit, we can pull them outside of the limit. So that becomes the sine of x times the limit as h approaches 0 of cosine h minus 1 over h, plus cosine of h times the limit as h approaches 0 of sine h over h. And what you're about to see, if you are wondering, why did we focus in on these two specific limits when we were practicing limits back in the limit videos and the limit unit? It's because we need them for this exact video. All right, so the limit as h approaches 0 of sine h over h, I know that's equal to 1. And the limit as h approaches 0 of cosine h minus 1 over h is equal to 0. So I can just substitute those values in, and so that becomes sine x times 0 plus cosine x times 1. Sine x times 0 goes away, and cosine x times 1 is equal to cosine of x. So what we see is that if we want to take, if we're thinking about the sine function and we want to take the derivative is equal to cosine of x. All right, and we will see, I don't know the verify, but what we'll do in the next video is we'll kind of take a quick look at it and we'll kind of convince ourselves that that's an answer that makes sense. And fortunately, it's a very elegant one, that sine and cosine functions are related to each other, not just because one is a phase shift of the other, but because their derivatives are so closely related to each other.